In this video, we are going to cover the concept of recursion. Recursion is one of the different styles of thinking to solve a specific problem. This is a problem-solving technique in which function calls itself. This may sound a little bit weird, but we can solve complex-looking problems using this approach. In recursive solutions, we have usually two branches. One is base case and another one is the recursive case in which the function calls itself. When we are using recursion, we have to make sure that the problem is slowly decreasing in size. Let's take a look at some example. We are going to take a look at factorial example. Here I have shown this factorial function which takes a number. We want to find the factorial of this specific number. In mathematics, if we want to find a factorial of any number, we can multiply all the numbers starting from that number up to the number 1. So for example, factorial of 5 will be 5 multiplied by 4, 3, 2 and 1. Similarly, factorial of 4 will be 4 multiplied by 3, 2 and 1. So we can see a pattern. Factorial of 5 can be calculated. We can use this approach to solve this problem recursively. So here in this factorial function, I have this base case where if the number is 1, then I return 1. If the number is anything greater than 1, that means I can return the number itself multiplied by the factorial of a number which is 1 less than the original number. Let's take a look at an example control flow. If I ask for factorial of 5, in order to calculate the factorial of 5, I can multiply 5 by factorial of 4. Now again, this 4 number is not equal to 1, so it will return 4 multiplied by factorial of 3. And this way we can recursively go through all the function calls, and finally when the number reaches 1, that's when the stack starts unwinding. That means we can find the factorial of 1. In this case, if n is 1, then it will return 1. So it will be replaced by the value 1. And again, to find the factorial of 3, we can multiply 3 by factorial of 2. And so on. We can go through all the steps and ultimately we can find the factorial of 5 as 120. So this is how the execution flows in a recursive function. Recursive function calls itself, so it will have to keep track of the local variables in the stack memory. Let's understand this code in practical demo. We can find factorial of any number using this equation. Like if we want to find the factorial of n, we can multiply n with n minus 1 factorial. We can use this logic to find the factorial. Let's see how we can define a factorial function to find the factorial iteratively. This factorial function takes a number n, and in order to find factorial, I just need to write a local variable product with a value of 1. And inside this function, I can iterate through all the numbers which are between 1 and n. So I write range 1 to n plus 1. In each iteration, I'm going to multiply that number with this product variable and assign it to this product variable like this. Finally, I can return this product variable. Now, if I check factorial of 5, then it should return 120. Now let's look at the recursive solution for the same problem. I will use the same function name. This takes n. And for a recursive solution, as I mentioned, we need to have a base case and a recursive case. So in this case, the base case is going to be when we reach the number 1. If number is equal to 1, then we return 1. Otherwise, we have to return the number itself multiplied by the factorial of n minus 1. And this is all we need to do. This else block is also called the recursive case. Let's test our function. If I test it with factorial of 5, I get 120. Let's verify this by using Python, and I get 120. So this way you can see that this factorial function, which is recursive solution, is little bit more elegant than this one. In this we have to make sure that we are iterating through 1 to n plus 1. Whereas in this recursive solution, we simply have to think about this equation. Let's take a look at another example. In this case, I want to find the Fibonacci number at a specific position. Fibonacci series actually starts with numbers 0 and 1. Every number that follows this number will have the value which is equal to the sum of previous two numbers. So the next number will have the value which is equal to sum of 0 and 1. So it will be 1. The next number will have the value equal to 1 plus 1, 2. The fourth index position will have the value equal to 1 plus 2, 3. Similarly, we will have 5, 8, 13 and so on. This is continuously progressing series. Now, if we want to find this solution in a recursive manner, then you can see that if I want to find the solution for this specific index, then I can find it by using the earlier two numbers. So this way we can solve the problem in terms of itself. In this case, our base case is going to be when the index is 0. That's when we return 0. Or if the index is 1, then we return 1. Otherwise, we simply return the sum of last two Fibonacci numbers. Let's try to implement this. I'm defining a function named Fibonacci. This takes a variable n. This is the index position for which we want to find the Fibonacci number. Let's write the base case. In this case, we will have two base cases. If the index position is 0, then we return 0. If the index position is 1, then we return 1. Now comes the recursive case. We have seen that if the number is neither 0 nor 1, then we need to find the Fibonacci numbers of previous two numbers. So in this case, we can simply return Fibonacci of n minus 1, and I can add the Fibonacci at n minus 2. And this is all we need to write. Let's test it out. Let's try to find Fibonacci number at index position 3. 3. And it returns true, which is correct. If I try Fibonacci at index position, let's say 10, then it returns 55. If I try Fibonacci at, let's say, index position 8, then I get 21, which is 8 plus 13. So this way, we can find Fibonacci number using recursive solution. Now let's say I want to find the Fibonacci numbers up to first 10 index positions. In that case, I can call this function 10 times. I can write a for loop for I in range 10, and inside this loop I can simply call this Fibonacci function, and to separate each of those numbers I am providing AND keyword argument with couple of spaces. Let's execute this and we get the first 10 Fibonacci numbers. So this way we can use the recursion to solve complex looking problems. Let's understand the pros and cons of these recursive solutions. If we take a look at our solutions for Fibonacci series as well as for factorial, then we can see that it makes for an elegant solution for complex looking problems. Sometimes recursive solution tends to be very elegant. That's the main benefit of recursive solutions. But there are few disadvantages of using recursive solution for a specific problem. First of all, when we start solving any problem, it may be very difficult to understand that problem in a recursive manner. Also for other developers, it can be difficult to understand. As I mentioned, recursive solution has to keep track of all the local variables in the stack memory, and that's why it tends to be memory intensive. If we were calling a factorial function on a large number, it would have kept all the function calls in stack memory, and probably it might result in a stack overflow error. If not implemented correctly, recursion can also result in very difficult bugs. This may become very difficult to understand because we don't have the exact idea on what variables are stored in stack memory. Overall, recursion is one of the controversial topics in programming, and this is one of the approach to solve a complex problem.